So in today's lecture, we are going to discuss more about three-phase delta connections. So how the phase current and the line currents are related in a delta connection, what is the phasor diagram for the delta connection, and so on. And finally, we will take up one or two numerical examples too. Okay, let's begin. Delta connection. Okay, so we know that in delta connection, you will have a mesh kind of thing, right? A closed path. Whereas in a star, you have only a node. Okay, so these are called lines. What I'm drawing right now is called line. Okay, so these are the three phases. Let me mark them as A, B, C. Okay, so the three phases are phase AB. What do you mean by phase? Phase means coil or winding. Okay, phase means coil or winding. Okay, so the three phases are phase AB, phase BC, and phase CA. Okay, and these lines that are extending away from the vertices A, B, and C, they are the lines. Okay, this is line A, this is line B, and this is line C. Okay, so these three coils are identical. That means voltage generator will also be identical. Okay, so voltage between the two lines, they are called the line-to-line voltages, right? So since it is symmetric, the voltage will also be displaced. They will be equal in magnitude and displaced by 120 degree. Okay, so what do you mean by line voltage? Line voltage is the voltage between two lines. Okay, so if you see voltage between lines A and B, okay, that is nothing but voltage across the phase AB. Okay, similarly, voltage between two lines B and C is same as voltage across the phase BC, and voltage across line AC or lines C and A is same as voltage across the phase winding C. So that means in a delta connection, line voltage and phase voltage are equal. Okay, so mode VAB is equal to mode VBC is equal to mode VCA, right? That is nothing but V line, and it is same as VPH. Okay, so in a delta connection, the line voltage magnitude is same as the phase voltage magnitude. Okay, now if we assume ABC phase sequence, ABC phase sequence. Okay, what will be your VAB? Your VAB will be VPH angle 0, VBC will be VPH angle minus 120, and VCA will be VPH angle minus 240. Okay, so again, you can represent them in phasor form. This is VAB. Okay, keep in mind, I always take VAB as reference. Okay, that does not mean that you have to always take VAB as a reference. You are at liberty to take VBC also as a reference. Okay, no worries in that. So if you are taking VAB as a reference, this is VAB angle 0, this is VBC at an angle of minus 120, and this must be VCA. Okay, so which phasor is to be chosen as reference is user dependent. Okay, so if you want, you can take your VBC as your reference. Okay, so if VBC is a reference, then this will be your VAB. Okay, and this will be your VC. Okay, so how will be ABC phase sequence? If you are taking VBC as a reference, your VAB will be what? If this is the case, your VAB will be VPH angle plus 120, VBC will be VPH angle 0, and VCA will be VPH angle minus 120. Why? Because we assume that the machine is rotating, the rotor is rotating in anti-clockwise direction. So if you take a point here first VAB will come, then after 120 degree VBC will come, then again after another 120 degree VCA will come. Will reach the reference point. Okay. So since the voltages are symmetric, since the system is symmetric, okay, the phasor sum of VAB, VBC, and VCA will become 0. It's evident. Okay, so phasor sum of line voltages are 0, right? So this is the case about a symmetric supply, delta connected supply. Okay. Okay. Now let us take the case of a load, a balanced delta connected load. Balanced delta connected load. Okay. What do you mean by balanced load? Balanced load means all impedances are equal. Okay. Equal in magnitude and equal in phase. That's the meaning of a balanced load. Okay. Say this is at angle phi. Okay. Or before that, let me mark something. These are the lines. Okay. This is point A, this is point B, and here is point C. Okay. So between point A and B, I have phase is at AB. Okay, which is nothing but Z angle phi. Okay, Z angle phi. I call this as ZBC, which is again nothing but same as Z angle phi, because I'm considering a balanced load. Balanced load means loads which are equal in magnitude and equal in phase angle. Similarly, between ZCA, we have ZCA, which is nothing but Z angle phi. Okay, all the load impedances are equal in magnitude as well as angle. Right. So this is a load. That means current will be flowing towards the load. Okay, so let this current be IA. This is the current IB, and this is the current IC through the three respective lines. Okay, so IA, IB, and IC are line currents. Line currents. Okay, what are they? IA, IB, and IC. Okay, these are the line currents. Now you see what happens upon reaching this node, the line current, it will split into two. Okay, it will split, right, as per Kirchhoff's current law, right? So let this be the current division: IAB, IBC, and IC. Okay, fine. Now, so what? So let us assume ABC phase sequence here. Okay, ABC phase sequence, right? So what will be VAB? VAB will be VL angle 0. Okay, keep in mind in a delta, V line is same as VPH in magnitude. Okay, line voltage and phase voltage are equal in magnitude in a delta connection. So whether I write VPH angle 0 or VL angle 0 does not change the things. Okay, it is one and the same, right? And what is VBC? It is VL angle minus 120, and VCA is nothing but VL angle minus 240. Okay, so AB, VAB means this thing. This is VAB. Okay, this is VBC, and this is VCA. Okay, so now you see current is flowing. What happens after reaching here? It splits into two. So you can apply what is KCL. Okay, so phase currents. What are the phase currents? So I can calculate what are my phase currents here. I know the phase voltage. Okay, it is same as the line voltage. Line voltage is same as phase voltage in a delta connection. Okay, so let us find our phase currents. Phase currents. What do you mean by phase currents? Phase currents are those which flows through a phase winding. So IAB, IBC, and ICA are phase currents, whereas IA, IB, and IC are line currents. Okay, so I can write phase currents are IAB, IBC, and ICA. Okay, so what will be phase currents in terms of voltage and impedance? I can write my IAB. What will be IAB? VAB divided by ZAB. And how much is VAB? VAB is VL angle 0 divided by, what is ZAB? Z angle phi. So you get VL by Z angle minus phi. Okay, VL by Z angle minus phi. Why is phi negative here? Because the lagging power factor. We have considered a lagging load. Okay, an inductive load, right? We know in an inductive load, current will lag the respective voltage by some angle phi. Okay, if it's a purely inductive load, current will be lagging by an angle of 90 degree. Okay, here it is an inductive load. That means R plus JXL. Okay, so there is some angle phi minus phi. Now what will be IBC? IBC will be VBC divided by ZBC. Okay, so VL angle minus 120 divided by Z angle phi. How much is that? VL by Z angle minus 120 minus phi. Okay, And similarly, what will be ICA? ICA will be, phase current ICA will be VCA divided by ZCA. So that means VL angle minus 240 divided by Z angle phi, or you get VL by Z angle minus 240 minus phi. Okay, so these are the phase currents. So one thing you can observe, what's the magnitude of the phase current IAB? VL by Z. What's the magnitude of IBC? VL by Z. And magnitude of ICA is also the same. So that means IAB, magnitude of IAB is equal to magnitude of IBC is equal to magnitude of ICA, that's equal to IPH. Okay, the phase current, right? So we have seen that IAB, IBC, and ICA are the phase currents, and IA, IB, and IC are line currents. So now let us find what are the line currents. Line currents. Okay, now at node A, you apply KCL. Okay, KCL at node A. What do you get? Sum of currents, and what is Kirchhoff's current law? Algebraic sum of currents at a node must be 0, or sum of currents entering a node must be equal to sum of currents leaving the node. So what are the currents entering? IA is entering and ICA is entering. Okay, and IAB is leaving. So that means IA plus ICA must be equal to IAB. Okay, or what is IA? IA will be IAB minus ICA. Okay, what is IAB? We had already found VL by Z angle minus phi minus what is ICA? It is VL by Z angle minus 240 minus phi. Okay, how will you solve this? I can take VL by Z angle minus phi common. So that means 1 angle 0 minus 1 angle minus 240. If you do this, you will get root 3 VL by Z angle minus 30 minus 5. Minus 30 minus 5. Okay. Keep in mind, what is VL by Z? VL by Z magnitude is IPH. So I can write this as root 3 IPH. I can write this as root 3 IPH angle minus 30 minus 5. Okay. Now, apply KCL at node A, B. KCL at node B. What do you get if you apply KCL node B? IB is entering and IAB is entering. So IB plus IAB must be equal to what? The leaving current IBC. So I can write IB plus IAB equals IBC. So that means what is IB? IBC minus IAB. Okay, but what is IBC? IBC is somewhere we had found. What is IBC? IBC is VL by Z angle minus 120 minus 5. So I can write this as VL by Z angle minus 120 minus 5 minus of what is IAB? IAB is VL by Z angle minus 5. VL by Z angle minus 5. Okay, so here again, let me take VL by Z angle minus 5 common. What will you get? 1 angle minus 120 minus 1 angle 0. Right? So you will get root 3 VL by Z angle minus 150 minus 5. Right? And what is VL by Z? VL by Z is nothing but the current magnitude. So I can write this as root 3 IPH into angle minus 150 minus 5. Okay. Now similarly, if you apply KCL at node C, what will you get? IC plus IBC equal to ICA, right? Or IC will be equal to what? ICA minus IBC. Okay. What is ICA? ICA is this VL by Z angle minus 240 minus 5. Minus 240 minus 5 minus IBC. IBC was we already found VL by Z angle minus 120 minus 5. Okay, so we will take VL by Z angle minus 5 common. So what do you get? 1 angle minus 240 minus 1 angle minus 120. Okay, so this turns out to be root 3 VL by Z angle 90 minus 5. Okay, and this is nothing but root 3 IPH angle 90 minus 5. Okay, so now you see, so what is IA, IB and IC? They are all line currents. Okay, IA must be equal in magnitude to IB to IC, and that must be equal to IA. Okay, what is that? That is nothing but root 3 times IPH. Okay, it must be the root 3 times the phase current in magnitude. Okay, now all the system is symmetric, the system is balanced, so that means currents are also displaced by 120 degrees. Okay, you can see here the difference between the current angles is 120 degrees. So now we are going to draw the phasor diagram for this. Okay, so let us first draw what is the voltage. So this is VAB, this is VBC, and this is VC. Okay, these are the three phase voltage or line voltage, because in a star, V line and V phase are one and the same. Okay, let us take a lagging load. Say IAB. Okay, this is 5, right? Similarly, this is IBC, lagging by an angle 5. Similarly, this is IC, lagging by an angle 5. Okay. Now, so what is IA? IA is nothing but IAB minus ICA. Okay. So IAB we have, where it is IAB is here. Where is ICA? Opposite to that. That means this thing. Okay. So phasor sum. Okay. So this will be the line current IA. Okay, so you see what's the angle between this? What is the angle here? It was minus 30 minus 5. Okay, so this angle is minus 30. This angle is minus 30. Okay, angle between IAB and IA, that is minus 30. Okay, similarly, what is IB? IB is nothing but IBC minus IAB. Where is IBC? IBC is here and IAB is opposite to that. Okay, so this is minus IAB and phasor sum. Okay, so this will be line current IB. Okay, so line current IB is also lagging the phase current IBC by an angle of 30 degree. Okay, this is 30 degree, right? Similarly, what is IC? IC is nothing but ICA minus IBC. Where is ICA? ICA is here minus IBC. So IBC is somewhere here. Okay, this is minus this thing. So this is somewhere here. Phasor sum. This will be IC. Okay, so this is the phasor diagram. Okay, so what is the conclusion here? So let us write. So what is the angle between these line currents, between IAB, between IBC and between ICA? It is 120 degree. Okay, so it's just a few points we will note. Line currents are 120 degree apart. Okay, then see, each line current is behind the phase voltage, behind the phase current by an angle of 30 degree. Okay, then line currents are 30 degree behind the respective phase currents. Okay, they are 30 degree lagging, we can see. So here this is ICA. Keep in mind, we have taken positive phase sequence. That means the rotor is rotating in anti-clockwise direction. anti-clockwise direction. Okay, so you take here the point here. First IAB will come after 30 degree. IA will come. Then IBC will come after 30 degree. IB will come. Then phase current ICA will come after another 30 degree. The line current IC will come and reach the point. Okay, so line currents are 30 degree behind the respective phase currents. Okay, now what is the angle between the line current and the line voltage or the voltage? It is, how much is the angle? 30 plus 5. Okay, because in a delta connection, line voltage and phase voltage are same. So the angle, the net angle between the line voltage VAB and the line current IA is 30 plus 5, because this is 5 and this is 30 degree. Okay, so if it's a lagging power factor load, okay, the angle between the line currents, the angle between the line currents and the corresponding line voltages and the corresponding line voltages is 30 plus 5 with current lagging. Okay, if current is leading, it will be the other way around. Okay, it will be 30 minus 5. Okay. Now, what will be the power, total three-phase power? How will you find that? How will you find total power? Total three-phase power will be what? 3 into power per phase. Okay, so if we know VPH, IPH, phase voltage and phase current, we can write 3 into VPH, IPH, cos of angle between the two, right? 3 into, in a delta connection, we know VPH and VL are same, into, how are IPH and IL related? IPH is nothing but IL divided by line current divided by root 3. So into IL divided by root 3 into cos 5. Okay, so you get root 3 VL IL cos 5 watts, power in watts, active power. Okay, let us try one of few examples now. Question: a 220 volt three-phase voltage is applied to a balanced delta connected load, three-phase load of phase impedance 15 plus J20 ohms. Find the phasor current in each line. Find the phasor current in each line. What is the power consumed per phase? What is the power consumed per phase? What is the phasor sum of the three line currents? What is the phasor sum of the three line currents? Okay, so a 220 volt three-phase voltage is applied to a balanced delta connected three-phase load of phase impedance 15 plus J20. Okay, ohms. Find the phasor current in each line. What is the power consumed per phase? What is the phasor sum of the three line currents? Okay, so we are given what is 220 volt? That is the line voltage. Okay, and we know in a delta connection, V line is same as VPH. Okay, so V line equal to VPH is given as 220 volt. Okay, now what's the next step? We have to assume a phase sequence. So for ABC phase sequence. Okay, so if you want, you can draw a figure also just for a better clarity. A, B, C. Okay. Is that AB, Z, BC, Z, C. Right? What's the question? Question is to find the phasor currents in the line. Right? Find the phase current in each line. That means you have to find the line currents. Okay. Where the line currents are IA, IC, and IB. Okay. So we have to find IA, IB, IC. What are they? Okay. So how can we find the line currents? We know the line currents are related with the phase currents. Okay. So if you can find the phase current, then you can calculate what will be the respective line current. So what will you do? We know the value of phase voltage. Okay. So let us take phase voltage VAB. That will be how much? 220 angle 0. VBC will be what? 220 angle minus 120 for ABC phase sequence. And VCA will be 220 angle minus 240 volts. Okay. Impedances are given. They are all equal. Okay. So if you convert that into polar form, you will get ZAB as ZBC and ZCA as that I didn't convert. Okay, you can convert that. So you will get 15 plus J20 ohms. Okay, now we can find the phase currents. Phase currents. What is phase current IAB? Phase current IAB will be phase voltage VAB divided by phase impedance ZAB. So when you do the calculation, you should get 8.8 angle minus 53.13 ampere. Okay. What will be IBC? IBC will be VBC divided by ZBC. Okay. Keep in mind it's a balanced system. So magnitude will remain the same and there will be an angle difference of 120 degree. So you can simply add minus 120 to minus 53.13. You should get minus 173.13 ampere. Then what is ICA? ICA will be VCA divided by ZCA. So you should get 8.8 angle. You add another minus 120 to this. You will get minus 293.13 ampere. So now we have found all the phase currents. So how will you find the line currents? Line currents. Right? IA. What is IA? IAB minus ICA. Okay. Just substitute IAB value you know, ICA value you know. You should get 15.2420 angle minus 83.13 ampere. Then what will be IB? IB will be IBC minus IAB. And that should be 15.2420 angle 156.87 ampere. What is IC? ICA minus IBC. That should turn out to be 15.2420 angle 36.87 amperes. Okay, so these are the phase currents in each line. Okay, now what's the next question? You have to find how much is the power consumed per phase, not the total three-phase power, power consumed in each phase. Okay, so how will you find that? VPH, IPH, cos phi. Okay, what is VPH? 220. What is IPH? 8.8 into cosine of 53.13. Okay, so that should that should be around 1161.602 watts. Or otherwise, how can we find that? IPH square RPH. Okay, IPH square RPH. Okay, so you can that way also you can find, right? Or it is IPH square RPH. What is IPH magnitude? 8.8. So 8.8 square into RPH. How much was the RPH? It was 15 ohms. Okay, into 15. That should also be same. Okay, and when you add all the phasor currents, what will you get? It must be 0. Why? Because it is a balanced symmetric system. Okay, so that's all about the delta connection. Okay, thank you.